Let's jump straight forward into Kepler's third law. Kepler deduced the relationship between the time a planet takes to complete a revolution around the Sun and the distance of such planet to the Sun. In order to derive it, let's go back to considering a planet revolving around the Sun in a circular orbit, just for simplicity. The centripetal force imposing that motion is the force of gravity, which is equal to the mass of the planet times the centripetal acceleration. The velocity is equal to 2 pi the radius over the time to complete one revolution. We can simplify this expression. I will square the right-hand side term. Then I move all constants to the left-hand side. I multiply by t squared and I find that the square root of the period is proportional to the cube of the radius of the orbit. This is for a circular orbit. For an elliptical orbit, we change r by a, the semi-major axis of the orbit, and get Kepler's third law as the square of the orbital period of a planet is proportional to the semi-major axis of the orbit. It is with Newton's equations that we can get this proportionality constant. But look at this equation. On the left-hand side, we have some constants. G, the universal gravitational constant, and pi, which is related with the orbit. We also have the mass of the Sun. Then we have T and A. This tells us that given the distance to the Sun, the period is given. It does not depend on the mass of the planet. There is a given period for a given semi-major axis, a given distance. Measuring the period is relatively simple, and measuring the distance too. So, if we look at another stellar solar system with several planets, by observing the distance of the planets to their star and their periods, we can measure the mass of a distant star. This is a cool method of weighting stars. Let's weight the Sun. To do so, we will use the data of the 8 planets in the solar system, not Pluto in this case. We need only to consider the semi-major axis and the orbital period. Here we need to be careful with the units. These are not SI units, so let's better change them into SI units. Now I will use the equation from Kepler's third law and solve for the mass of the Sun. Well, better, I will write an equation for a straight line, for a linear expression. What I have here is an equation with 2 variables, t and a. I can plot a cubed versus t squared. The slope is going to be this constant here. If, as the horizontal variable, I use g over 4 pi squared times t squared, that's my new variable, instead of just t or t squared, then the slope will just be the mass of the Sun. Let's do it then. Let's plot these two x and y new variables, and we will only need to look at the slope, and from there that will be the mass of the Sun. The blue dots are the observational data. The red line is the linear fit to those observational data. And the equation is the linear regression, where the slope is 2 times 10 to the power of 40, and this is the mass of the Sun in kilograms. And that, my friends, is how we weight stars. May science be with you.